But am I audible clearly? Can I start?
Yes, now it is fine. You can start.
Okay. So my now okay, I will take roughly 40 minutes, maybe, or maybe 45 minutes. Okay. So my talk is on alkali-based molecular SIMS, an innovative chemical approach for the exact composition analysis of quantum structures. I worked at the Surface Physics and Material Science Division of Saha Institute of Nuclear Physics, Kolkata, India. This is my institute building, where most of the works have been carried out at my laboratory. And to start with the quantum structures, let me start the very basic things that a quantum structure means. The electron is confined within a very small dimension of a couple of nanometer size. For example, an electron, if it is confined in a potential well of length a couple of angstroms only, few angstroms, then the electron will have oscillations, and the electron will have a discrete energy levels. So it will not have any continuum in the energy states. So, and as we know from the very basic physics courses, that the energy of the electron in the potential well, it is at the nth quantum number is n square h square by 8 ml square. So it is the energy of the electron for the nth quantum number. And you can see, depending on the value of n, 1, 2, 3, 4, 5, and so on, we are having discrete energy states, energy values of the electron in the quantum well. So that means the electron, if it is if it is confined within a small dimension, then the electron is confined and the energies are quantized. And if n equal to 1, then the energy is h square pi square, n equal to 1, h square divided by 8 ml square, or in other words, h cross square by pi square by 2 ml square. So if I convert h into the reduced Planck's constant, then h cross will come. So this is the positive value of the energy, which is actually not 0, which is the energy, the minimum energy for n equal to 1. So this is in contrast with the classical system. In a classical system, the particle can have 0 energy by resting it motionless at the bottom of the box. But in quantum mechanics, energy cannot be 0, because the minimum energy, what I have just now shown you, is h cross square pi square divided by 2 ml square. So this is the very basic thing of quantum structure, where the energies are quantized. The particles are quantized, and the energies are quantized. And for the quantum confinement, we can actually see. So it is the uncertainty principle, and from the uncertainty principle, we can immediately get the momentum. The uncertainty in momentum is h divided by delta x. Delta x is the uncertainty in position. This is the very basic uncertainty principle, and from there we can convert the momentum in terms of h cross h by 2m f square. So energy we know p square by twice m is the energy. So the E confinement, basically in E confinement, it comes about h cross square by 2m delta x square, where delta x is the spread in the value of the position of the electron in the quantum box. Okay. Now delta x is the uncertainty or the quantum size. That means the minimum size, the size which is actually needed to confine an electron, that should be delta x from the uncertainty principle, and that is actually given by h cross square by 8 divided by m kb T, where kb is the Boltzmann constant and T is the temperature in the Kelvin scale, half of the square root of that, which is nothing but the de Broglie wavelength. So the de Broglie wavelength, you can see the quantum size effects are prominent at a room temperature, when the delta x, or the size effect, the minimum size, or the size of the dimension, that is equal, or rather equivalent to the de Broglie wavelength. Now we can see there are three basic types of quantum confined structures. For the bulk, we know there is no confinement, so the number of free dimensions is 3. So electron can move in all directions, x, y, z directions. And for the quantum well structure or superlattice structure, I'll be talking in superlattice in a minute. And then for a quantum well structure, an electron is confined. Electron is actually free to move in 2 directions. So electron is restricted to flow in 1 direction. So it is basically confinement is only 1 direction. And in the quantum where the electron is able to move in only 1 direction, and electron motion is restricted in 2 directions, and number of free dimensions is only 1. And for the quantum dot or quantum box, electron can move neither in x direction, nor in z direction, nor in y direction. Electron is confined within a very, very small region, is called a quantum dot. So where the number of free dimensions is practically 0. And these kind of structures, I will come back in a minute, this kind of structure can be grown in the laboratory. So by the molecular beam epitaxy or metal organic chemical vapor deposition. Now this is a energy diagram of a quantum structure. This is the growth direction, and this is the, you can see this is the gallium arsenide. Gallium arsenide is sandwiched between 2 aluminum gallium arsenide. As we know, gallium arsenide is having a lower band gap compared to the band gap of aluminum gallium arsenide. So we are doping aluminum in gallium arsenide. So when you dope aluminum in gallium arsenide, actually the band gap increases. It's called the band gap engineering. So band gap can be engineered by suitable control of aluminum into the gallium arsenide. And if you just now see the energetics, you can see this is the bottom of the conduction band where electrons are confined, and this is the top of the valence band in the gallium arsenide, and this is the band gap of the gallium arsenide, and this is the band gap of the gallium arsenide, aluminum gallium arsenide. Similarly, this is the band gap of the aluminum gallium arsenide. So it means we are in the laboratory like aluminum gallium arsenide. We are growing aluminum gallium arsenide on gallium arsenide, and again aluminum gallium arsenide, and we are making a quantum well structure. Quantum well structure. Am I audible? Am I audible?
You are audible.
Okay. So, so basically, as you can see, the density of states in the quantum structures. I've talked about the 2D structure, the quantum well structure, but basically we can grow quantum where structure or quantum dot structure or quantum well structure. And this is the bulk structure. You can see if you talk about the bulk for the density of states, the density of states is a very important parameter to understand the quantum structures. This is the only parameter, the density of states. The density of states, I'm not having that much time to go on the density of states, because I have lots of slides where I can talk about many hours in how to calculate the density of states for the different quantum structures. But only, I'm just telling you, this is the density of states for a bulk structure, and this is a function of energy. As a function of energy, the density of states is a parabolic nature for the bulk structure where there is no confinement of the electrons anywhere. And if I just confine in one direction, an electron is allowed to flow in XY plane, for example, like a quantum well structure, electron motion is restricted in the Z direction, then the density of states become a staircase structure. Very important to understand these things, how the electron energy of the density of states can be a staircase structure. And for the quantum where it's like the delta function type of nature. Okay, for a single quantum well, where you can have a single delta function, and if you have a multiple number of quantum where structure, then you have multiple number of density of states as a function of energy. So there are like a delta function structure. And when you are ending to the quantum dot structure, the density of states become just like the energy as a function of as a function of energy. They are simply like the discrete energy values, very sharp energy values at a particular at different points. It is very similar to the atomic shells. Okay, the electrons when they are confining at atomic shells, to the K, L, M, and etc. So similarly, we are having the density of states in a quantum dot structure. Now, this is a graphene structure. This is a 2D structure. Ideally, a graphene, graphene is an aromatic rings of graphene, which is extending into 2 dimensions. And if you calculate, very simplistically, if you can calculate the density of states, it becomes ml square. L is the length of the confinement divided by pi h cross square. As I mentioned already, h cross is the reduced Planck's constant. This is interesting to understand that density of states is not dependent on the energy anymore. So it is an irrespective of the energy. So that means density of states is not dependent on energy. So it means you can have a plateau of energy. If you make a plot of the density of states as a function of energy, you will expect the electron achieve a constant plateau of energy. But actually what happens when the electrons are achieving enough energy, they can jump into the next available subband. However, in a particular subband, electrons will remain at a constant plateau of energy. So it means you will have different subbands, and in each subband, electrons can have a constant plateau of energy. So it means you are having a staircase structure. You can see you are having a staircase structure for a quantum well structure. Now we are preparing this quantum well. Similarly, you can have the density of states in a 1D structure e to the minus half. It means like a delta function. Okay. Now I will not go into the details anymore. As you can see, this is the density of states for the bulk, the density of states for the quantum well structure. Electrons are flowing in the XY plane, and so the density is like a staircase structure. When you are making it same material, when you make the quantum well structure, then you are having the number of delta functions, as I already mentioned. And if you go to the quantum dot, you are having the discrete energy values, very sharp energy values. Now we are actually going to the actual topic of my talk, where we are preparing a quantum well structure. Actually, that is a silicon germanium quantum structure. Actually, we are making a quantum well like gallium arsenide, aluminum gallium arsenide quantum well structure, and also we are making a superlattice structure. These are all quantum structures. A superlattice structure means there are a number of periodicity in 2 materials. We are growing silicon on germanium, then again silicon, again germanium, again silicon, again germanium, and this is a periodicity going on for many layers, and there could be 100 layers, there could be 200 layers. So, and the gallium, the material having lower band gap, has to be thinner than compared to the silicon. And if you have a multiple layers like this, a periodicity where the periodicity has to continue, in that case, where we are basically having a superlattice structure. And in the superlattice structure of silicon germanium, why it is important, I will tell you in a minute. You know, silicon is an indirect band gap semiconductor, because electrons and holes, the positive holes in the valence band and the negative electrons in the conduction band, they are not able to recombine so easily, because the position of the bottom of the conduction band and the position of the top of the valence band, energetically they are not in the same the horizontal, same vertical line. So naturally the jump of the electron to capture the jump of the electron to occupy the whole position, that is a recombination. This combination is difficult. In that case, some sort of media, they have to do this kind of recombination. They have to do with the phonons. So this kind of annihilation is possible through the help of phonons, which is important. But actually, because it is an indirect band gap semiconductor, this it is a very bad light emitter. So it is an inefficient light emitter because there is no possibility of a direct transition of electron into the hole to make a recombination and to have a light emission. You can imagine this. Same thing happens for the germanium, which is also an indirect bandgap semiconductor. Now, what is interesting to make you understand that is a quantum confinement effects can happen in silicon. If the silicon size is squeezed in the form of a quantum structure, a low dimensional structure. For example, a silicon could be a porous silicon. We know that silicon can be a porous. Silicon can be silicon nanocrystals, silicon quantum dot, or as I am now going to talk about, is like silicon germanium superlattice structure. That kind of, if we can prepare that kind of confined systems with silicon, then light emission could be prominent from silicon. Even if it is an indirect bandgap semiconductor, we are having enough, or rather quite prominent light emission even at the room temperature. Now, why it is happening? Just let me talk about it, about the physics. The quantum size, the quantum dot size is very small, is smaller compared to the excitonic Bohr radius. You know Bohr radius. So when the quantum size, dot size is smaller than the exciton Bohr radius, the excitons are squeezed, leading to the quantum confinement effects to dominate. Then the electronic and optical properties are highly tunable. And here what happens, two fundamental quantum effects are occurring. One is a band gap, because the silicon size is reduced. We are reducing the quantum, we're making it a quantum effect. So where band gap is increasing and the conservation of momentum breaks down, because the localization of the charge carriers in space leads to the delocalization of the in momentum space. I'm not going to talk about the momentum space and so on, but I think everybody know about it. So consequently, silicon nanocrystals that can have emission properties depend on their size and will behave as a quasi-direct bandgap semiconductor. This is an interesting phenomenon, that if you can prepare a silicon germanium superlattice structure or a thin multilayered structure, then it can be converted into an indirect, from indirect to a direct bandgap semiconductor, and we can have a prominent light emission at the room temperature. Now, I'm not going to talk more about the physics behind it, but what I'm going to talk, that the method or the methodology what we are following is an epitaxial method to grow silicon germanium superlattice structure. This is basically a schematic diagram of a molecular beam epitaxy device, where you have a substrate and you have a metallic stainless steel chamber. This is a very big chamber, and inside the chamber, this is an extremely ultra high vacuum, 10 to the power minus 12 millibar pressure, and there are number of effusion cells or the Knudsen cells where we are keeping different elements at the different Knudsen cells or effusion cells, and by heating we are evaporating the materials, and in a molecular form they are flowing, and they are depositing on the substrate, and we are controlling the different elements one after another simply by a computer controlled setup. And the entire machine is a computer controlled setup, and we are actually making the epitaxial growth, layer by layer growth. This is important to understand. This is a layer by atomic layer growth. It's an extremely controlled method of deposition of the thin films in a multi-layer or a multi-layered structure or a superlattice structure or a quantum structure, quantum well structure, simply by an epitaxial method, by layer growth. What is happening? We are actually evaporation, or the vaporization is basically, the vaporization is so controlled and so small evaporation rate. Basically, every individual atom is taking some time to settle down on the substrate. and the second atom is coming. So basically, it's a soft landing of the atoms or the molecules on the substrate, and the substrate is actually revolving, rotating here, and it is a cryo panel because the whole panel is at very low temperature, and we are actually monitoring the epitaxial method by read gun, the reflection high energy electron diffraction gun. Anyway, and this is the machine. This is the machine, the MBE machine. What has been it is installed in our laboratory. This is a quite sophisticated machine, and you can see this is the big chamber where I mentioned there are all efficient cells, and the epitaxial film of a quantum structure is being grown inside that big chamber. Okay, and this is a computer control setup. Okay, I will not go into the detail many more, but as you can see, this is a simplistic diagram of aluminum arsenide and gallium arsenide, a quantum structure. This is a quantum well structure. You can immediately see the aluminum gallium. This is the aluminum arsenide, and this is the gallium arsenide. You cannot distinguish the atomic configurations. You are not able to distinguish because the atomic arrangement in aluminum arsenide, they are in the line with the atomic arrangement of the gallium arsenide. So this is a crystallographic orientation. So the film what you are growing, they are following exactly the crystal orientation or crystallographic orientation of the substrate. And each and every substrate, every film has a very extremely symmetric. The atomic arrangement is symmetric. Now, depending on the lattice constant differences, it can be a homo or hetero structure. It can be a homo structure. If we grow silicon on silicon, it is a homo structure, and if we grow a germanium on silicon, it becomes a hetero structure. Okay, now we are going. This is the third part of my talk, that we are going to now quantify the material, quantify the elemental composition, or quantify the composition in the quantum structure using the ion beams. Now we are using SIMS technique. It's a secondary ion mass spectrometry, and I'm going to talk about that, and I'm going to talk about the matrix effect in SIMS and how the matrix effect can create a difficulty in quantification, and then how we are able to compensate the matrix effect by using a molecular SIMS. And then the molecular SIMS can be MCS. The M is an element of interest, and CS is a cesium ion. This MCS means it's a molecule consisting of one atom of the element. For example, silicon, if we talk about, then silicon and the cesium. Cesium is the ion beam, what we are using for the primary bombardment. Okay, now cesium plus is a singly charged cesium, and the cesium plus and the M, they are combining to form a molecule, and we are detecting this molecule in the SIMS process, and we are quantifying. Okay, I will talk about that. Now, in the SIMS, we have to just tell very briefly what is happening. We are selecting primary ions, a particular primary ion. It could be oxygen, or it could be argon or krypton, whatever it is, but mostly we are using argon, or we are using oxygen or cesium, depending on the mode of operation. Now, when the ion beam is impinging in the material, is being incident, you can imagine the ion beam, a single ion can go inside in the material, and these are the atomic layers. Okay, these are the atomic layers, and the single ion can go on in the material, and they can make collisions with the target atoms, and you can have a primary collision, and the primary collisions can initiate the secondary collision, and so on and so on. So you can basically have lots of collisions. Okay, so you can have a collision cascade. So there are many collision cascades are being generated within the material, and what happens, a part of the collision cascade can reach the top surface from the beneath. Okay, and if the remaining energy of the collision cascade is overcoming the surface binding energy, some of the atoms sitting on the top layer, they can be ejected. Okay, so these are the atoms, neutral particles, neutral atoms. Now, almost 99.999% of particles which are emitted from the top layer or from the top second layer. So they are the neutral particles, but a small, very, very small fraction, maybe 0.0001% of the total amount of particles could be ionized, either positive or negative. So these positive or negative ions, now the secondary ions, we are detecting by a suitable detector. But of course, we are making the mass analysis, because the secondary ions could be either molecule or the singly charged or the doubly charged. So depending on the M by E, so the specific charge, we are selecting out the by the energy separation, by an energy separator. We can select the energy and we can create an energy window, and then we can make a mass analysis to select out a certain particle of a certain mass, and we are able to detect. So basically we are getting a spectrum, and we are getting the intensity of the secondary particles, secondary ions. Now this is basically a top surface phenomenon. As I mentioned, the collision cascade can go inside, but basically the sampling region, what we are measuring the particle or the ion emission from the top surface, okay, or top 1 or 2 or 3 monolayers. So it is basically a very, very surface phenomenon. Okay, as you can imagine, it's a surface phenomenon, and that's why the surface chemistry is important in the ionization phenomenon, because if it is a positive ion, the positive ion, what is being emitted when it is in the close proximity of the top surface. So the chemistry of the top surface can influence the ion, and ionization probability can go down or can go up depending on the surface chemistry. I'll be talking in a minute. Okay, so now so you can see the secondary ions are now mass analyzed and then followed by the detector, and so we are detecting. Now I have to say two important things, that we can actually control the primary ion current, what is impinging on the material, and if it is extremely small, like picoampere per centimeter square, then we can have a low erosion rate, and we can really make the top surface analysis, because only monolayer can remain, basically because the top surface atoms are ejected. So basically you are eroding surface layer as a function of time. I think you understand what I am meaning. So if the atoms are ejected from the top layer, from the top atomic monolayer, then naturally, if all the atoms are ejected from the topmost atomic monolayer, then naturally, if the bombardment goes on, the second monolayer is hitting. So the second monolayer atoms are ejected. Similarly, the third monolayer, and basically you are getting, as a function of time, you are getting the current, the secondary ion current as a function of time. So it is the static sims. The static sims means the primary ion current is very small, and then you can probe the surface analysis, do the surface analysis. And the dynamic sims, and in the dynamic sims, the primary ion current is quite high, and you have higher erosion rate, and you can do the depth profiling. As you can see, the primary current is the static sims, where you can have the primary current is very, very small, and you can basically confine to the top monolayer. Okay, the bombardment goes on over a period of half an hour or 2 hours or 3 hours, but basically you are confining on the top monolayer. But in the dynamic sims, you are basically going down and down and down. You are etching the monolayer after monolayer, and you are getting the emission as a function of time. And you can probe the material anywhere located somewhere inside, and you can get the concentration as a function of time or as a function of depth. Okay. Now I will quickly go to the analysis. This is the schematic layout of a top sims, time of flight sims, and this is for the dynamic sims. This is basically the mass spectrometer is a quadruple type. Okay, now I will this is the main instrument where we can get the secondary ion mass spectrometry, and we can do the secondary neutral mass spectrometry measurements. I will just take 5 minutes to give you that the secondary ion current is basically a function of the concentration. You can see the concentration Cx. So X is the elemental concentration Cx. It is the fractional concentration, which is proportional to the current, secondary ion current. Okay. Now the secondary ion current is linearly proportional, but the problem is this beta. The ionization probability is something which is coming in the picture, and this is making the whole process complicated, because the secondary positive ion or the negative ion emission cross section, as I mentioned, they are changing abruptly with the chemical composition of the top surface. And because the beta X, the emission probability of the positive or negative ion is changing abruptly depending on the top surface chemistry, your fractional concentration is difficult to measure from the secondary positive or negative ion current. So that's the process. I'm not going into the details of the physics, but I will just talk about that. That basically we are getting some kind of the composition analysis. I would show you that we are using MCS phenomenon, that we are using cesium bombardment. We are doing cesium bombardment, and the cesium combining with the neutral M, which is emitted, and basically they are, you can see, as I'm going once again, as you can see, this is basically this electric field of the ion, electric field of the cesium ion is polarizing the atom, sputtered atom, and it's making a dipole moment, and then the electric field of the ion, probing ion, electric field of the incoming ion is actually interacting with the dipole moment. Okay, and this is polarization. You see the polarization, the dipole moment is proportional to the electric field, and this is the atomic polarizability. Now, atomic polarizability is the main factor what plays the most important role in the the time is short, so I have to quickly go that we are measuring the MCS, we are measuring the MCS2, and we are actually, I can show you that we are actually getting different kind of structures. We are growing by either by the MBE or metal organic chemical vapor deposition is a chemical phenomenon, or even simply by magnetron sputtering method. So this is a gold copper multi-layered structure. Okay, this is the cross-sectional TEM. Okay, and this is, we are measuring by the SIMS. You can see that across each interface we are getting different kind of alloy formation, and different kind of alloy formation, they are actually separated spatially. So we can actually pinpoint which kind of alloy is forming because of the intermixing of gold and copper at the interface. Okay, so at the interface, you can imagine that gold and copper, they can intermix across the interface, and they can prepare different kind of alloys, and the compositions can be extracted through SIMS. And we can even get a different kind of structure which is not conventional, and that structure could be some kind of, you see, some kind of Cu3Au, which is a non-conventional, unconventional or metastable alloy position, which is also possible to get in the interfacial layer because of the interfacial strain. You can imagine copper gold, they are creating interfacial strain because they have the lattice mismatch. And quickly I will go, this is a gallium arsenide, aluminum gallium arsenide, a multiple quantum well structure. We are getting aluminum concentration through the SIMS, and we are actually measuring the aluminum concentration as a function of depth. We can pinpoint absolutely correctly by the MCS process. As I mentioned to you, that by using the MCS, we can absolutely quantify the quantum wells. And I will show you that this, even for an alloy structure, this is a superlattice structure, silicon germanium superlattice structure, and where the electron density can be extracted through the X-ray reflectivity. The blue lines are the X-ray reflectivity, and the red lines are the SIMS, okay, secondary ion mass spectrometry. And you can see the positions of the peaks either in the SIMS you see the SIMS profiling and the positions of the peaks in the profiling of the X-ray reflectivity, they are perfectly matching, okay. And from that we can extract the electron density. This is the first time electron density has been calculated from the SIMS experiment from using the MCS molecular SIMS. And from this Avogadro number, and this is the atomic number. Zm is the atomic number, and Cm is the fractional concentration as a function of Z, and Am is actually is the mass number of the atom. Okay, so we know everything, and so the concentration. If we know the concentration, we can find out the electron, or if we measure the electron density, we can find out the concentration. And this is the XRD spectrum, and I will show you quickly that actually for the silicon germanium superlattice structure, as a function of time, and we are getting the compositions of silicon and germanium. The compositions of silicon germanium in an alloy, for example, this is an alloy structure, and you can see the compositions are perfectly matching with the compositions measured by the X-ray, measured by the X-ray, the electron diffraction. Okay, electron diffraction. So this is you see the intensity of the germanium cesium concentration, germanium cesium, to the intensity of the cesium silicon. So if we measure this kind of molecule, simply the ratios of the intensities, they are proportional to the concentrations of germanium and silicon in a matrix of silicon germanium alloy, for example. And once again, if we measure the MCS2 molecule, like while there are two cesium atoms with an M sputter, so this is the MCS2 molecule, even more higher molecule, then we can get a one-to-one correspondence with the fractional concentrations. And finally, I will talk about the imaging. That imaging is possible, that you can simply image the structure by the focused ion beam. And we can see this is a titanium nitride spider web pattern on silicon with 1 micrometer size, minimum feature size. So this is a perfect image what has been obtained through the secondary ion mass spectrometry. And this is done using a 45-degree electrostatic sector energy filter. And this is a high efficiency screen extraction system for the optimum ion collection. And this is once again another image, aluminum image, showing the concentration of aluminum at the grain boundaries of a lanthanum strontium copper iron oxide. So this image has been imaged. This practically image has been done, extracted through the SIMS imaging. Okay, this is another one, as you can see, which is secondary electron image, and this is secondary ion image. As you can see, the secondary ion image is almost comparable or even better magnification for a silicon ion image. So this is an FIB. So fast ion bombardment is possibility of using making a microscope is called the FIB microscope, using the secondary ion mass spectrometry and using the molecular SIMS. As I mentioned in the beginning, we are making a microprobe fast ion bombardment a microscope. So we can get an image of a very fine pattern, a nanoscale pattern, basically a microscale pattern. And finally, we can get an image of gallium. This is using the gallium ions from a liquid metals. We can get a SIMS image of a copper grid structure. This is a copper grid structure of 100 micron holes and 30 micron bars. This is a grid structure using gallium ion beams from a liquid gallium ion source. Thank you very much for your attention.